So I'm going to be talking about Assume UTXO, which, if you're unfamiliar, is kind of a little scaling project I've been working on for a few months now. And just out of curiosity, by show of hands, who has heard of this before? Okay, cool. So maybe like half of you. That's maybe more than I would have expected. All right, so what are we talking about here? Basically, if you've done IBD recently, you've probably found that it takes anywhere from 4 hours with really awesome hardware and a great connection to maybe a few days if you've got like an ancient rusty spinning disk and something resembling 56K dial-up. So that's kind of an unfortunate variance because it basically means that in many cases, if you want to get onto the Bitcoin network and if you want to start transacting, then the setup time is non-trivial to do so in kind of a trust minimized way by using Bitcoin Core or a client that directly connects to the Bitcoin network rather than going through some proxy like Electrum. So this is kind of unfortunate, and it basically means that anybody who's a non-hobbyist likely isn't going to run a full node. In fact, there's a buddy of mine in the audience who shall remain nameless, but he's a longtime Bitcoiner, and he has yet to set up a full node, and he kind of gives himself grief about it a lot. But I can understand because it's kind of onerous. So Assume UTXO is kind of a way of making this process a little bit more manageable without compromising on the security of Bitcoin to a significant degree, and without imposing any huge additional storage burdens on nodes. So how does this actually work? The idea is basically that, let's see, who's familiar with Assume Valid? Okay, kind of. The basic idea behind Assume Valid is that there's a block hash hard-coded in Bitcoin Core, and it basically says the software that we recognize as Bitcoin Core, the consensus engine, has previously validated a chain containing this block hash, and the block hash is buried sufficiently deep so that to actually kind of fabricate work on top of it would be sort of infeasible. So basically during the initial block download, when we're grabbing blocks, checking that they're valid, we can kind of skip signature checking for all blocks up to this height. And so this value typically gets updated once per release. So it's always buried under a few weeks worth of blocks at the very minimum. So that's so Assume UTXO would be kind of an extension of this same principle, and we'd basically do it for a snapshot of the UTXO set, so that we're skipping not only signature checks but block deserialization and download up front, so that we can get a node operable kind of as soon as possible. So the exact way that we do this is that we'd obtain some snapshot somehow from possibly a peer, but I'll talk a little bit more about that later. The bootstrapping node is going to get the headers chain, and then it's going to basically ensure that the block that the snapshot was taken at has a corresponding entry in the block headers chain that we download. We're going to load the snapshot, and then we're going to basically fake a blockchain up to the point where the snapshot begins. We're going to take a content hash of the deserialized UTXO contents, and this is really key here because we're going to make sure that it checks the hard-coded Assume UTXO value in the code. And this is a content hash that basically ensures that you've gotten a snapshot that corresponds to the thing that you expected to. And then from there, we're going to do a brief initial block download to get to the network tip. And right now, at least the snapshot that I've been testing with basically gets you 90% of the way to the network tip. So it's basically foregoing 90% of the work that you'd have to do to get current. And then, crucially, we start a background validation process with a separate data structure that we can basically use to do an initial block download in the background to validate fully up to the point of the snapshot while we have a kind of operable node that's current with the network. Once that background chain state hits the base of the snapshot, we compare the hashes of the UTXO sets at each point, and we just make sure they connect up. So now, God willing, I'll do a brief demo with the caveats that in the actual code, we're hard coding Assume UTXO values that are valid for mainnet. So I've commented those out, so we can just do a quick demo here. and basically introduced a small RPC command called monitor snapshot that just basically shows you the state of the snapshot or the assumed valid chain state and the initial block download chain state. So you can kind of see what's going on with each of them, hopefully, but it might actually move kind of fast here. So we'll see how that goes. Oh. Okay, so I'm going to run a script here, and basically what it's going to do is it's going to set up two nodes. One of them is kind of pre-synced to a height of 30,000, and basically it's going to take a snapshot at that point at 30,000, and then it's going to IBD 6,000 more blocks to create a difference between the snapshot and its tip. And then I'm going to start up another node. I'm going to load the snapshot into that node. So that's going to kind of deserialize the snapshot and then initiate at 30,000. And then it's going to IBD the remaining 6,000 from its peer. And then it's going to go and start the background validation of that snapshot. So let's see if we can start that. Really should have done this beforehand. So basically, this is just going to print out the debug logs of the server and the client. Okay. Okay, so we're actually creating the snapshot here on the server. I think the server is booting up still.
Can you increase the font size a little?
Yeah. Is that any better? Maybe a little bit better? Okay, so now the server is IBDing that additional 6,000 blocks just to create a difference between the snapshot and the network, quote unquote. So it's done that, it's shutting down. Now we're starting the server back up. Okay, so when I hit enter here, basically what's going to happen is you're going to see some log lines, and then you're going to see the output of that RPC I talked about, where you can kind of see the state of both the snapshot chain state and the IBD chain state as the client comes online. Okay, cool. So you can see here the snapshot chain state is adding blocks from 30,000 up, and it just hit the tip. So now we've gone back to the IBD chain state, and we're doing the back validation there. And as soon as that completes, which it just did, the IBD chain state actually gets thrown away because we no longer need that data. That was just to validate that the snapshot's actually there. Cool, so the demo actually worked. Okay, so this seems all well and good. You know, we're cutting out 90% of the upfront work. Surely there must be some horrible trade-off that I haven't yet revealed. This can't be safe. You can't get something for nothing. What's the deal here? Okay, so here's the rub, basically. What this makes easier is if someone wants to give you a poisoned binary, it makes it really, really easy for someone to say, okay, I want to fool Jonas into thinking I have a coin when I don't. So I'm going to create a bad UTXO set, serialize it, take the hash of that, and then I'm going to change the hash in the binary. I'm going to give the binary then to Jonas, and I'll be able to fool him. The thing is, yes, that's practically easier, but in our security model, if we assume that you've gotten a compromised binary, you're already toast, because there are a million different ways to basically fake coins once you have control of a binary. So in a sense, this is just a pretty direct extension of assume valid. I mean, with assume valid, I think there's the added complexity of if you did give someone a bad binary for that, basically you'd have to mine a block on top of the last assumed valid block, which you know is non-trivial, or the last checkpointed block, which is non-trivial work. But again, if you were giving someone a bad binary, you wouldn't change assume valid. You would change like the Ccoins cache view to basically return a coin under certain special circumstances. So I think this one trade-off that we're kind of making here is a perfectly reasonable one, and in our threat model, attacks. But hey, if you come up with something great, let me know, because I'm kind of curious. A few sort of more minor points here. When I was initially throwing this idea around with a few of the other devs, one of them said, well, hey, why are we even doing this background validation thing? If you're willing to buy into this reduced, quote unquote, reduced security model, for the, say, 4 hours to 3 days that you're operating under a snapshot chain state, like, why even do the background initial block download? And this kind of raises an interesting point about the motivations for this, even beyond just convenience. If you think about it, the blockchain is obviously a data structure that grows linearly over time. We expect and we hope that this thing will just continue on into perpetuity. And so it's really infeasible to have something that just gets longer and longer and longer. And so we need some kind of approach that basically truncates the amount of time that it takes to get synced to network with reasonable security. That said, I still think that for now doing a background validation is really important, if not only because I think if you didn't do the background validation by default, then you might have this situation where basically every node on the network is running pruned and nobody's distributing early blocks. Again, I think that's something that we may encounter at some point, but for now it's easy just to leave this background validation thing in and do it. There is additional resource overhead, given that basically we've got all the separate data structures running around to do 2 blockchains at once, which I'll get into a little bit here. Another person asked why we don't just Bitcoin Core, do something with compact block filters, BIP 157, and certainly that would be one way to do it. I think kind of counterintuitively, that's more of an engineering effort than it is to do this thing, because as we're going to see later, doing this basically just amounts to doing some refactoring with a few additional logic updates to the net processing code and the wallet code. So this, in some sense, is actually easier to do than implementing an SPV node within Core, because there's no existing code to do that. We can do some third-party thing, like Casa, I guess, is shipping with pre-filled data DIRs, and BTC Pay is doing something called FastSync, which basically is trusting some group of developers to sign a snapshot of your data dir. I don't think that's great. I don't think we want that. Basically, too few people already scrutinize the single thing that the security of Bitcoin relies on, which is the core code base. We don't want to go around introducing additional dependencies that people have to go out and audit. That just doesn't make a lot of sense to me. And then the final sort of question here is, like, should we wait for some kind of a consensus commitment? Because, say, if we were to take a hash of the UTXO set and then embed that in every single block header or something, obviously then we wouldn't have to trust the binary to give us a valid assume UTXO hash, but we'd be trusting miners. The real problem here is that introducing a consensus commitment, as you all probably know, is hairy business, and it's a lot of work, and we don't really want to do that unless we're absolutely sure that we're committing to the right data. And I'm going to actually talk about the data that we should commit to, because it's kind of complicated. It depends on how we're going to store and distribute these snapshots. So to that point, there are basically 2 phases of this project. The first one, which is pretty much complete at this point, is enabling this functionality, but in a very kind of subtle, not sort of flagrant way through the RPC. So basically giving an RPC command called load TX outset that lets you manually load in a snapshot at startup. And so basically only people who are competent enough to fool around with the RPC interface would be using this. And the idea is to basically just get this out into the wild, have people playing with it and trying to break it, and to actually see if it's a useful mechanism. And then in the second phase, we basically build in a distribution mechanism to the peer-to-peer layer. But what's interesting about this is that because the security model is kind of a content-based hash, it sort of doesn't matter where you obtain the snapshot from. You could do it over torrent, you could do it over some CDN, HTTP thing. It really doesn't matter. But that said, I think it would be nice to have something in the peer-to-peer layer, because then you're really not, you don't have to tell someone to go out and fetch something from a third party. It just kind of is bundled with the software and served by your peers. So I think that's important. Basically, the way that phase 1 breaks down is we have to do some refactoring, code shuffling around for multiple chain state usage. We have to code the creation of snapshots and the activation logic. There's some, like I said, minor net processing change. And for those unfamiliar, net processing is basically the part of the code that adapts the incoming network messages to the validation layer. The validation layer is kind of what decides how to append to the chain, and obviously network messages come from your peers. We have to do some juggling with pruning and cache management, and we have to introduce some RPCs. By the way, if any of this goes over your head, you want to stop me and ask questions about Bitcoin in terms of how the code's organized, please do so. This is kind of a sort of out-of-date diagram, but mostly correct at this point of the kind of changes that we have to make. I won't go too deep into details, but basically the gist is previously we had a bunch of global state and a bunch of functions in this validation unit that people would call into, and it kind of presumed that there was just one chain state. Now, obviously, because we're going to have the kind of active assumed valid chain and the background chain, we need two of these things running around the system simultaneously. So that just kind of amounts to doing better encapsulation of things within these chain state objects, not using so many globals, and having an object called the chain state manager that kind of provides an interface for interacting with multiple chain states. So it's really not a huge deal. A lot of the work is done so far for this. I'd say there's still about 2,000 lines of change outstanding, and maybe more if I decide to do some much needed, in my opinion, lock splitting, but that's another story for another day. In terms of what we have to do to the wallet, basically the changes are a lot more minimal than I thought they would be. All we have to do is prevent the user from rescanning, which is a process where you're going over the chain to see if there's any information in there that's relevant to you based on the addresses in your wallet. We just have to basically throw an error if the user attempts to rescan for an address that's beneath the height that you took the snapshot at. Obvious reason being that you don't have the blocks to actually do that rescan. In terms of caching, you may or may not know that a lot of caching happens in Bitcoin Core, and actually the performance of your node is dependent on a setting called dB cache. And that basically indicates the number of megabytes that you are willing to allocate to Bitcoin that it can grab from your memory and cache the UTXO set in. And so now, because we have two chain states, we have to divide up this fixed cache somehow. We don't really want to introduce like a dB cache 2 parameter. And so there's just a little bit of work around basically when we divide up the cache. On snapshot load, because it's effectively IBDing to tip as fast as possible, we allocate 100% of the cache to the snapshot tip. And then 30-70 split, where basically to do tip maintenance, the snapshot chain has 30% of the cache, but a lot of the work is really going on in the background on the initial validation chain. So maybe that might be a 30-70 split, that might be a 5-95 split, I'm not sure yet. I gotta run some tests. And then finally, when the background validation chain completes, obviously you can reallocate all the cache to the tip. This is just some code showing some cache juggling. I don't know why it's in there really. And then in terms of pruning, this is a little bit complicated. As some of you may know, pruning is a setting you can configure your node with, where if you have limited storage requirements, basically it discards old blocks kind of within some window that you specify. The lowest you can go is like, I think 550 megabytes. But this does change pruning a little bit because we've got obviously something at the tip and then something kind of historically back there that needs access to old blocks. So we got to make sure that we don't prune the blocks that are needed for the validation chain. But luckily, because we don't expect any reorgs in the validation chain, or else something's horribly wrong and we should just like stop and catch fire, we don't really have to. We can prune pretty aggressively on that chain, so we can keep maybe a window of like 5 blocks, which is negligible in terms of storage. Like I said, there's some net processing changes. Basically, there's just like one data structure that we've got a namespace by chain states to make sure that if you only have one peer, that you can kind of keep track of what your last common block is with that single peer without the chain states stepping on each other's toes. That's not a big deal. And then in send messages, basically there's like, if you're talking about net processing, maybe this is a little bit in the weeds, but if you're talking about net processing, there's like 2 main identities in there that are really important in terms of procedures. There's process messages, which takes all the incoming messages off of the network and processes them somehow. And then there's send messages, which is kind of like a proactive loop that says, okay, should I send this message out to my peers? Who should I talk to? and so forth. And so basically all this is saying is that when we're trying to figure out which blocks to download next, we just kind of have to wrap that in a loop that takes into account all the chain states that we care about. So honestly, pretty basic stuff. There's some initialization shutdown stuff that you probably don't care about, I probably don't want to talk about, but that's basically it. So in terms of the second phase, this is kind of where it gets really interesting and where I haven't done a whole lot of work yet, but we've got some good ideas. The idea is basically that these snapshots right now are about 3.2 gigs, and obviously that size is variable based on how many UTXOs there are. And we not only want to be able to provide the latest snapshot to our peers, but let's say a historical peer boots up with like a much lower assumed UTXO value at a lower height. We'd still like to be able to service those peers with snapshots within some reasonable tolerance. So we probably want to keep around maybe 2 historical snapshots on top of the active one. And this means that you're talking about burdening nodes with like 10 gigs of extra storage. That's not ideal. And additionally, we've got the problem that if you want to distribute these snapshots over the peer-to-peer network and you're naively sending around multi-gig blobs, well, that kind of spells denial of service. So we have to figure out some way to not only kind of mitigate storage requirements, but make transmission feasible. And one way of doing this that's kind of interesting is something called forward error correction. And for anybody not familiar with this, basically it's kind of a magical technique where you take a piece of data, you slice it up, you pick some checksums, and you do some matrix multiplication, and you end up with a set of data that's larger than your original set of data. But the key here is that you can lose parts of this data and still reconstruct the original data. And again, that involves some matrix multiplication, some inversion stuff, but that's not really important. The upshot is that we could come up with a scheme where peers slice up each snapshot into some small series of data fragments, and then they generate this reconstruction padding, and that would allow you to basically find any unique peers and then just obtain from them their shards of the data, reconstruct this thing, and then you've got your snapshot. So this is kind of fault tolerant relative to like if you just striped the data kind of naively, because if each peer had like its own stripe of data, you could kind of DOS snapshot bootstrapping by picking one stripe and just knocking them off the network. So this is a kind of cool way of dealing with that I have yet to code. Who's heard of UTree EXO? Okay, cool. Yeah, UTree EXO is an awesome project. To try and describe it in 20 seconds is futile, but I'll give it a shot. Basically, UTree EXO turns the representation of the UTXO set from a hash map into a kind of arbitrarily small Merkle forest. And the idea there is that instead of when you get a transaction and you want to say, okay, is this valid? Let me check the inputs. Instead of going and looking those up in a map, the sender would basically package some Merkle proofs along with the transaction. And they would basically say, okay, take your Merkle roots and then just check that this proof works out. So the really cool upshot of that is that you can, instead of dragging around this 7 gig map when it's finally deserialized in memory, you could have something that's a few kilobytes. That's pretty awesome. Why is that awesome? Well, because when we're doing the initial block download, we could basically slice the chain up into separate partitions and then kind of simultaneously do a bunch of them and then just check that they all kind of match up. So like with legacy IBD, you start at Genesis and then you just sync linearly all the way to tip, and you have to wait till you get to tip. With assume UTXO, you can just like start maybe 90% of the way through, get to the end, cool, and then in the background do the rest of the chain. With assume UTXO plus UTree EXO, if anybody has any cool way of marketing that name, please let me know. You could slice this up into sort of arbitrarily small chunks, maybe based on your processing capability or whatever. So I think that's pretty cool. This is not a sure thing, and I think I'm probably going to be trying to work with Tradeoff in the next few months to see if it's feasible, but it's kind of promising. Okay, so what's next in this project? Had some stuff merged for phase one. At this rate, it's going to be like sometime next year that gets finished. I hope it's quicker than that, but maybe not. Got to think about how to do online snapshot generation because that's kind of a complex thing. Right now, a lot of time is spent in Bitcoin Core basically just flushing the in-memory cache out to disk. And so we have to kind of figure out how to do that either a lot faster or in an asynchronous way, because in order to generate these snapshots, we have to persist everything to disk. We got to figure out how to deal with copying level DB around maybe, which would be unfortunate, but I don't know, maybe we can do something smart with level DB snapshots. And we have to, like I said, we have to decide on a storage structure for phase two, because we maybe want to do this like where we slice it up into chunks, and then maybe we want to Merkleize it so that when you're sending snapshot chunks to your peers, you can attach a little Merkle proof and say, hey, this is actually the data you're looking for. Don't know yet, got to figure that out. And then there's some like sort of refactoring sort of performance stuff that you can get out of this in terms of like splitting up some of the locks. If any of you have looked around the code base, you know that CS main is like the lock to deal with, and it would be nice to kind of break that up, reduce contention a little bit. And I think that's it. So if anybody has any questions, hopefully I can answer. Really? Antoine?
Yeah, what's your target user, or if it's non-novice, is it for people with a smartphone, people with, I mean, just a dumb laptop, people more?
Yeah, I think initially I was thinking about people who want to use Bitcoin and want to sort of do the right thing, but you know, maybe the idea of waiting for like a day or two to transact is ridiculous. So you know, maybe if they have to wait 45 minutes or an hour, you know, that's a little bit more feasible. But I think, you know, if you think about like Bitcoin nodes being on point of sale systems, it would be kind of nice if, you know, you get the point of sale system delivered, you know, solved or whatever, and you know that's a separate problem with trusting the binary. But you know, the shopkeeper boots it up and it takes maybe an hour to sync or whatever. But you know, ultimately at some point it's doing that background validation. It's a full node, so that I think that would be kind of cool. But yeah, I mean, if things really get moving with UTree EXO, we can start talking seriously about like phone usage. I think that would be kind of interesting. The caveat with UTree EXO is that it actually one of the trade-offs is it increases bandwidth sort of considerably. So we'd have to think about that. But I think phones would be cool. Yeah, in the back.
Yeah, I was wondering if you could speak a little bit about what the advantages are to actually running the transactions and validating that way. Say you were to find an issue with a block, what can a non-mining node actually do to affect the kind of consensus process in that scenario?
That's a great question. Directly, I guess not much other than fork yourself. But obviously, you know, that would be a big realization, and you'd pretty readily want to communicate that out. I mean, odds are it would be something local to your system, but even if it weren't, you know. But I don't know. It's really hard to say. It's, you know, we debate a lot about whether that's just, or I debate a lot about whether that's just kind of a sort of abstract corner case. You know, if we really did find truly some you know, invalid transaction buried way deep. I mean, obviously that would be something that was probably local to you, because you know the rest of the network's validated our chain over and over again, probably millions of times. But yeah, that's a good question. I mean, it's kind of along the lines of like, if we had a reorg that went back like 3 weeks, you know, how would that impact confidence in Bitcoin? And I think if we have a 3-week reorg, it looks pretty bad. Luckily, I don't think the likelihood of that's very high. Yep, and then I'll get to you.
Do you ever foresee this becoming an opt-out thing, where if you get a full node, it syncs the checkpoint, and then it does the whole check for you, so you're at least up and running in an hour? Like, do you see the goal of this being sort of a default state, or is this always going to be an opt-in thing?
Yeah, it could be. I think for now, it's definitely, even when we get to distributing the snapshots in peer-to-peer, assuming we get there, I think it's going to be opt-in for a while. But I don't know if that goes off without a hitch for a significant period of time, maybe a whole release, maybe more, then maybe it could be a default because obviously I think part of the users we'd be targeting with this aren't people who specify configuration options, so it makes sense. Yep.
You had mentioned that UTXO commitment was tricky or theory. Can you please elaborate on that? Like, why was
Sure.
such a problem?
Yeah. So if we were to introduce a consensus commitment to a UTXO set hash, say, basically we'd want to be pretty confident in the structure of that hash, and the reason that that's important is because the structure of the hash dictates how we can generate the hash. And Fabian, for example, who's a resident here, has been working on something this summer called the rolling UTXO, or a rolling hash for UTXO sets, and that computationally is a lot easier to compute, or it's a lot more feasible because you're basically just kind of appending hashes into this thing, and it's kind of accumulating a value as it goes on. Computing something like that per block is a lot more feasible than hashing the entire UTXO set and using that as your hash. The problem with a rolling hash is that if we want to actually commit to, say, a series of Merkle roots that correspond to a forest, for something like UTree EXO, well, that's a different commitment structure than the rolling hash would be. And we don't really know if we want to use either of those at this point. And so I think basically we want to make sure initially that this is a viable approach in the first place. And then we want to get an intuition for what the right commitment structure is. And then, maybe only then, we could start thinking about how to commit that in. And then again, like that's, maybe that's some trust in miners, and so maybe that's not the right way to do it. Yep.
Are you able to speak to the relative risk that somebody would take by syncing with the end of the chain while waiting for the beginning to sync, and especially if it takes several days? You're working with not complete data, even though you believe maybe a snapshot is a good one. How much risk is involved here?
Yeah, I've tried to think a lot about the practical risks of this, and I really can't see any, for the only reason that the only way that you would perform an attack here is to basically modify the binary. And once somebody can give you a modified binary, you're cooked. So I can't think of another way that you would sort of attack this, because presumably the snapshot hash is going to be buried under weeks and weeks of work. And it's really, again, it's really kind of a spiritual extension of assume valid, which is already in Bitcoin. So yeah, if anybody has any practical attacks, like, I'd love to know about them, but I can't think of any.
You mentioned BTC-based fasting. Can you explain the difference between assume UTXO and fasting?
Yeah, that's a great question. So with fastsync, basically your Bitcoin node generates a data directory intuitively, right? It has to. Fastsync does is Nicolas Dorier at various points wants to be able to, rightfully so, wants to be able to get BTC Pay server users up and running very quickly, because typically, they're not, they're people who want to do commerce and not necessarily like worry about running a full node all day. So what he does is at various points, he'll take a datadir of his own, and he'll basically hash that datadir and then sign the hash and get a bunch of other people to kind of recreate the process of creating that datadir and sign it as well. So it's your trust model shifts from kind of the Bitcoin Core source code to the Bitcoin Core source code plus all the signatories of that datadir that Dorier generated. And I love Nicholas, he's great, but I don't necessarily want to have to rely on his GPG signatures to make sure I'm running what I think I'm running. So it just introduces an additional dependency that isn't Bitcoin Core.